I'd like to welcome you all here to Jefferson Lab. My name is Joyce Miller, and I'm a mechanical designer here at the lab. And I'm also the captain of the Jefferson Lab Dog Training Club. So if you were wondering how we got this important person from upstate New York to come to Hampton Roads, Virginia, I also have rescue greyhounds. And I follow a blog written by a fellow greyhound rescuer, and he wrote a little blog post about Mr. Orzel here, and he wrote this blog post about teaching dogs physics, and I thought, well, wouldn't that be a great thing to have here at Jefferson Lab? So I contacted our science education department, and they invited Mr. Orzel to come and speak to us tonight. He is a physics professor at Union College in New York, in upstate New York, where it's cold, much colder than here. And and he writes a blog, his own blog, and he also writes for Forbes, so you can look those up. And he has written 3 books, 2 of which are about teaching dogs physics. And so I'd like to introduce you to Dr. Chad Orzel, and he's going to be giving our talk tonight.
So thank you very much for the opportunity to come down here. It's really neat to get to see this facility, and I've had a very good time. So, and thanks to all of you for coming out on a school night. So I'm going to talk about talking quantum physics with my dog. So this is me, and that's my dog, and I'm talking to her about quantum physics, and she is listening raptly as dogs do when I start talking about science. So why is what is quantum physics, and why is it important enough that you should talk to your dog about quantum physics? Well, quantum physics is one of the greatest intellectual achievements in scientific history, and it's led to all sorts of fantastic developments. The very first quantum model is made by this guy, Max Planck. There's a whole set of institutes in Germany, major national science labs, that are named the Max Planck Institutes in his honor. Right. Niels Bohr, another of the pioneers of quantum physics, there's a Niels Bohr Institute in Copenhagen in Denmark. And there are other people who are less famous than those two. Maybe you've heard of him. Played a major role in launching quantum mechanics, the theory that we now know. All in all, in the first part of the 20th century, there's something like 20 Nobel Prizes handed out for discoveries relating to the development of quantum mechanics. So it's a really big deal in scientific circles. Right. And there are ideas from this that have caught on to such a degree that people and even some dogs have heard something about them. So these are very important, and I want to give you a bit of a flavor of what the book is like. This is a short video. It's a couple of minutes. This is a chapter from the book.
When Emmy trots in, tail wagging. "You should give me a treat," she says. "I should? Why should I give you a treat?" "Because I'm a very good dog, and I deserve a treat." "I'm not going to give you a treat for no reason, but I'll tell you what I'll do." I reach into the treat jar, then hold out both fists. "Guess where the treat is, and you can have it." Immediately, her nose starts working. No sniffing, either. I put my hands behind my back. "Just guess which hand has the treat." Okay, both." That's not one of the choices. "But it's the right answer. It's like that cat in the box." "What cat in what box?" "You know, the one in the box, with the thing. It's dead and it's alive at the same time, in the box." "Schrödinger's cat?" "Yeah, that's the one." She wags her tail excitedly. "I like that experiment. You should do that." For one thing, it's just a thought experiment to show the absurdity of quantum predictions. Nobody ever did it for real. For another, I doubt that people would appreciate it if we started killing cats. "I don't care about the killing. I just like the idea of putting cats in boxes. Cats belong in boxes." I'll pass that on to the scientific community. But what does this have to do with your treat? "Well, the treat could be in your left hand, and it could be in your right hand. I don't know which it's in. You won't let me sniff to see where it is. So that means that the treat is in a superposition state of both left and right hands at the same time. Until I measure which hand it's in, the answer is that it's in both hands at the same time. That's an interesting argument. It doesn't apply here, though. Yes, it does. It's basic quantum mechanics. Well, yeah, it's true that unmeasured objects exist in superposition states as a general matter. But those superposition states are extremely fragile. Any disturbance at all, absorbing or emitting even a single photon, will cause them to collapse into classical states with a definite value. Yeah, but people have seen them. Sure, there have been lots of cat state experiments done, but the largest superposition anyone has managed to make involved something like 1 billion electrons. That's nowhere near the size of a dog treat, which would contain something like 10 to the 22 atoms. And on top of that, even in the most extreme variant of the Copenhagen interpretation, the wave function is collapsed by the act of observation by a conscious observer. Now you can argue about who should count as a conscious observer. Not a cat, that's for sure. Cats are dumb. But by any reasonable standard, I count as an observer. I know which hand the treat is in, so you're dealing with a classical probability distribution in which the treat is in either one hand or the other, not a quantum superposition in which the treat is in both hands at the same time. Oh, okay. She looks disappointed. So, come on, guess which hand the treat is in. I still say both. Why's that? Because I am an excellent dog, and I deserve 2 treats. Well, yeah. Also, I'm a sap. I give her both of the treats. Ooh, treats, she says, crunching happily.
So these are some of the conversations I have with the dog about quantum physics. Now, in thinking about how to frame a talk like this, I tried out a bunch of different ideas, but one thing that I'm sure many of the people who work here at Jefferson Lab could confirm for you is, if you get known in the public as a physicist, you get some interesting email. And if you get known as a physicist who talks to a dog about physics, you get some even more interesting email. And so I thought I would share with you some email that we got about the book from interested readers. So, for example, here's a question. Here's a reader of the book. And here's a question. It says, Dear Dog Physics, I heard that quantum physics says that particles behave like waves. Does this mean that I have wave nature? Right? And this is, in fact, one of the things that quantum physics says. It says that everything in the universe, from light to electrons to atoms, behaves like both a particle and a wave at the same time. Right? That's kind of an amazing idea. And to explore what that means, first we really need to talk about what it means for something to behave like a wave. Right? So a wave is a disturbance in some sort of medium. Typically you think of them as things like waves in water. So here's this beautiful picture of a bee that's fallen into a puddle, and it's flapping its wings trying to get out. Right? And each of those wings is creating a disturbance that propagates out as a wave. So you see here's the bee's left wing producing waves that go out this way. Here's the right wing producing waves that go out that way. Right? What's a characteristic signature of something behaving like a wave? Well, if you look at the back of the bee, there's something complicated going on back here. And that's the really interesting part, the great part of this photo. Right. What's going on back there? Well, back there, here is where the waves from the 2 different wings come together. And when they overlap, they do something interesting. Right? How they add together depends on how they come together, where the peaks and the valleys are. So if these 2 waves come together in such a way that the peaks of one fall on top of the peaks of the other, right, they add together to give you really big peaks. Right? So you have these regions where you have extremely large waves radiating out. On the other hand, if the peaks of one wave fill in the valleys of the other wave, then they cancel each other out and you get nothing. And so there are these regions back here of basically still water radiating out from the back of the bee. This sort of pattern is characteristic of wave behavior. This is something that you see anytime you have waves going through multiple, coming from multiple sources. Right? Physicists typically will call this a double slit experiment. One of the simplest ways to do it is to take a piece of card and cut 2 narrow slits in it, look at some light. You can see this happen. What happens is the waves that come through each of the slits at some point in the center will come together so that the peaks fall on top of each other and you get a bright spot. You move out to the side a little bit, one of those waves has to travel a little bit of extra distance, right? There's an extra half a wave in there that makes the peaks of one wave fall into the valleys of the other, and that leads to a dark spot. Go a little bit farther out still, now the extra distance that the one wave travels is a full wavelength. The peaks fall on top of the peaks again, and you get another bright spot. Right, so the characteristic signature of wave behavior is this pattern of bright and dark spots going out as the waves are in and out of phase with each other. So that's what happens if you send waves from two sources and bring them together. Now what happens if you do this with particles? Well, we can think about something that's very definitely a particle. Okay, so we had the Super Bowl just a couple of days ago, so we can think about football. Right, a football is something that very definitely behaves like a particle. Right? It has one position and at any given time. All right, so imagine you're gonna try and kick a field goal, but we'll make this a little more physicsy. We'll replace the back of the end zone with a screen that detects where the football lands, and make this a little more of a challenge. But rather than having goalposts that you could doink one off, we'll set up a barrier with two slits cut in it. All right, so this is exactly analogous to what you do with the light to see this pattern of bright and dark spots. You can ask what happens if you do this with classical particles like footballs. All right, well, if you look at the screen, right, you send in one football, you detect one football. Right? It lands at a particular place at a particular time, and that's it. All right, but that doesn't give you a great deal of information because you couldn't necessarily predict that that specific ball would end there. You really need to repeat this experiment many times. So you do it again, and maybe it ends up over there. Right? And you do this over and over and over again, and what you find is it will trace out a pattern of exactly two stripes. All right? So these are footballs that went through the right-hand slit. These are footballs that went through the left-hand slit. Or, there might be the occasional one that heads into the right-hand one and ricochets off and ends up in the left. But basically, you get two stripes. All right? So this is the difference between particles and waves. Particles will give you two stripes if you send them through two slits. Waves will give you a pattern of bright and dark stripes. So what does it mean for a particle to behave like a wave? Well, here's a demonstration of this that we can do now. This is done by scientists at Hitachi who have an electron source that sends out one electron at a time. And they shoot that electron at a barrier with slits cut in it, and they look on the far side to see what happens. And each of these individual dots showing up in this video here is a single electron hitting a phosphorescent screen and being detected. And you see there's a pattern that looks, pretty much random. They're showing up all over the place. But the video speeds up a couple of times, and the rate at which these come in increases. And you can see a pattern starting to emerge of there are some places where you're more likely to see electrons, and there's other places where you're not likely to see them at all. Right? If you repeat this often enough, each of those electrons, though each electron is detected like a particle at a single spot at a single instant, all of them together trace out a pattern of bright and dark stripes. Right? That's exactly the same sort of thing that you see when you do this with light. So an electron is a particle that behaves like a wave at the same time. Right? This is the central mystery of quantum mechanics. Right? Richard Feynman famously said that everything weird about quantum mechanics is contained right there in that experiment. You send one electron at a time through a barrier with slits cut in it. It behaves like both a particle and a wave at the same time. And now this isn't just some odd property of electrons. You can do this with things that are much larger. Right? You could do this with molecules. All right, this is data from an experiment where people used buckyballs, these fullerene molecules that are shaped like soccer balls with 60 carbon atoms in them. They shoot those at a barrier with slits cut in it. On the far side of that barrier, they see a pattern of bright and dark stripes, indicating that those big molecules are behaving like waves. And they can get even bigger than that. These are some cartoons of horrible, giant organic molecules with unpronounceable chemical names that I will not attempt to render. But I will point out that this thing right here contains 430 atoms. And if you shoot that molecule at a barrier with slits cut in it, right, you see, it gets harder and harder to do as these things get bigger, but you still see characteristic wave behavior. So everything in the universe behaves like both a particle and a wave at the same time. Right. So, follow-up question from my interested reader here. So can I use my wave nature to help me catch bunnies and squirrels? Because this is the sort of thing that dogs want to do with quantum mechanics. And it's absolutely true that dogs have wave nature. Right? Dogs also have Buddha nature, which will do them about as much good when it comes to trying to catch prey animals. Right? Because the issue is the wavelength associated with a particle gets shorter and shorter the heavier that particle gets and the faster it moves. By the time you're talking about something the size of a dog, you're talking about a wavelength that's so incredibly short, there's no chance that you would ever measure it. Right? What do I mean by so incredibly short? Right? If you take an atom, imagine taking an atom, which we all learn in grade school looks sort of like a cartoon solar system, only it doesn't really. You take that cartoon solar system atom and you blow it up to the size of the real solar system. Okay? You scale everything around that atom up to the size of a real solar system. The wavelength of a dog walking across the room would be the size of a single atom within that solar system. Right? That's the difference in scale that you're talking about. That's how short the wavelength associated with a moving dog is. And that's why you'll never be able to see a dog behaving like a wave as it moves across the room, even though everything in the universe absolutely does have wave nature. Okay, so that's one aspect of quantum physics that dogs often ask about. Here's another question. I heard that quantum physics says that particles can pass right through obstacles as if they weren't there. Can I use this to get through the fence to the yard next door? All right. This is another obvious thing that dogs would be after, and this is another phenomenon that's very real. It's called tunneling. Right? And this is a phenomenon where sometimes quantum particles end up in places they shouldn't be able to get to. All right. So how does this happen? Well, again, let's think about an ordinary classical particle. We'll go back to thinking about a football. Right? You send a football up in the air, it goes up, it slows down, it turns around, it comes back down and falls, hits the ground, and bounces a couple of times. All right. Now, this is a characteristic motion everybody's seen before. All right. If we want to think about this in terms that we can compare to quantum physics, we need to talk about this as something that we can turn into a wave. We need to talk in terms of the probability of finding this football at a given position at a given time. All right. Well, we can do that by sort of turning this thing on its side. All right. So we can make a graph of the probability of finding the football at a given height. All right. And what you see if you do this classically is something that looks like this. Right, it goes up and then comes crashing down. Right, there's zero probability of finding the football below the ground. Okay, it's kind of obvious. And there's a maximum height that the ball reaches, and there's zero probability of finding the ball above that maximum height. All right, the probability of finding it somewhere in between, well, it goes up as you go toward the top because up here, the ball is moving very slowly. It stops for an instant at the top and then turns around. So there's a good probability of finding it there. In the middle, the ball's moving pretty fast as it goes on its way up and on its way down, so it doesn't spend very much time in the middle, so the probability is much lower there. All right, so that's the probability of finding a football at a particular height. All right. Now, if we imagine doing this with a quantum football, things are kind of similar. Right, that's the blue curve here. All right, this looks a little scarier because it's doing some wavy stuff, right? But it has to do wavy stuff because everything in the universe behaves like a wave. All right, but the general pattern is the same. Right, we've got wavy stuff, and the waves get bigger and bigger as you go toward the top, right? Just because the probability increases up there. All right, but the really interesting thing about this is this bit right here. Right, there's a bit above the maximum height where the probability doesn't come down to zero immediately, but tails off slowly. There's some reasonable probability of finding the ball in this red shaded region, which is higher than it ought to be able to get to, according to classical physics. And this is because the ball behaves like a wave. Right? Waves don't just immediately, instantly stop. Right? If you go to the beach and look at waves on the shore, they sort of ride up the shore. Right? The waves have to spread out over some distance. There's some extent over which the wave can be found in places it shouldn't be able to reach. And this is what drives the phenomenon of tunneling in quantum mechanics, right? Particles can penetrate through barriers that they shouldn't be able to get through. Right? Now, that's a weird thing to say, right? We don't see that happening, right? If I run at that wall, I'm not going to end up in the hall outside unless I physically go through the wall, and I don't have enough energy to do that. All right? But we know that this phenomenon is real, and I can prove it to you because the sun shines. All right? It was sort of nice for a little while today. Right? You could see the sun. All right? And the fact that the sun shines is proof of tunneling. All right? How does that work? Well, what's the sun doing? The sun is turning hydrogen into helium and releasing energy. All right. How do you do that? Well, hydrogen is basically a proton. All right. If you take two protons, you bring them close enough together, you can get them to stick together. One of them turns into a neutron in the process. It's nuclear physics, don't worry about it. All right. You take a couple of these guys, you can stick those two together, and you can form a helium nucleus that has two protons in it. Each step in this process releases a little bit of energy. This goes on a lot in the core of the sun. And that energy that's released heats the sun and turns into the heat and light that we receive from the sun, allows all of us to exist. All right. Now, this is something we can easily calculate what it takes to do this. Right? Because if you're going to try and bring two protons together, they're both positively charged. They repel each other. Right? They're going to try and push each other apart. They don't want to be really close together. But you can get them really close together if you throw them at each other really hard. Right? And you can calculate how fast you have to throw them at each other to get them to stick. And it turns out that corresponds to a temperature of 15 billion degrees. All right. And we know what the temperature of the core of the sun is. The temperature of the core of the sun is 10 million degrees. All right. Those are not the same number, right, by a factor of 1,500. Right? The sun is 1,500 times too cold for fusion to occur, according to this simple calculation. All right, so how does the sun shine? Well, most of the time when the protons in the sun come toward each other, they just separate. They repel each other and they go back apart. But every now and then, quantum mechanics allows these things, as they come close together, to just tunnel through that barrier and end up sticking together and releasing the energy that powers the sun. Right? This happens extremely rarely, but there's an immense amount of hydrogen in the sun. This is going on over and over and over and over and over again. Even though this process is extremely unlikely, it happens often enough to allow fusion to proceed and keep the sun shining. Right? So the fact that the sun shines is proof that quantum mechanics allows things to pass through barriers that they shouldn't be able to get through. So, right, does this mean that we're going to see dogs start, quantum passing through fences? No, because the probability of this happening has to do with the wavelength of the particles compared to the size of the barrier. And again, the wavelength of a dog is just too short for that ever to show up. So a follow-up question on this from this reader. So I should just dig a hole under the fence then. And that is also a kind of tunneling, but only bad dogs dig holes. All right. So one more question from a canine reader. I heard that quantum physics says that cats are both alive and dead at the same time. I've always known they were undead zombie monsters. Now my humans will have to believe me. Okay. This is a reference to the video I showed at the beginning of the talk. This refers to a thought experiment called Schrödinger's cat, named after this happy fellow here. This is the Austrian physicist Erwin Schrödinger. He was one of the pioneers of quantum mechanics, but he became disillusioned with the theory for philosophical reasons, and he left physics and left quantum physics and went off and studied other things. But on his way out the door, as it were, he invented this thought experiment to show what he felt was the philosophical absurdity of the theory. Right? And it goes like this. He said, imagine taking a cat, all right, and putting that cat in a sealed box. All right? You seal it up good so you can't see or hear what's going on inside the box. And in the box with the cat, you put some device that has a 50% chance of killing the cat in the next hour. And the question he posed is this. At the end of the hour, what is the state of the cat? Now, common sense would seem to say that, well, the cat's either alive or it's dead, right, inside the box. All right? But what Schrödinger noted is the mathematics of quantum physics tell you that the cat is not alive or dead. It's both alive and dead in equal parts right up until the instant that you open the box and check. Right? And that seems so completely absurd that he rejected the whole theory and decided he wanted nothing more to do with it. Right? If you want sort of a very slightly dated musical rendition of this, right? So here's, hey, I'm Schrödinger, and this is crazy, but here's a sealed box. The cat lives, maybe. So this is a really weird idea. It's also absolutely true. We know that quantum objects exist in more than one state at the same time. Right? How do we know this? Well, because of the experiment I showed you earlier with the single electrons. Right? We shoot single electrons at a barrier with slits cut in it, and each electron acts like a particle. It's detected at a single point at a single instant in time. But if we repeat this experiment many, many times, all of the electrons together trace out this pattern of bright and dark spots that's characteristic of wave behavior. How do you get that pattern with waves? You get that pattern with waves coming from two different sources. That means that during the course of this experiment, each electron behaves like a particle, right, but like a wave at the same time, and it's in two states. It's in the state of having gone through the left-hand slit and having gone through the right-hand slit at the same time. Those pieces come together, and that's what makes this pattern of bright and dark spots. So the double slit experiment done with electrons proves that quantum particles can exist in multiple states at the same time. Right. Now, does that explain zombie cats? Right? I mean, zombie cats might exist, but you can't really blame physics for them for the same reason that you can't see dogs tunneling through fences or demonstrating wave behavior. The wave nature associated with something like a cat is just too small for this to really show up in the everyday world. So while there might be zombie cats out there, it's not our fault in physics. I want to give you one final example of an email that we received after the publication of this book. And this one's a little different, but probably very familiar. So it's, Dear Dog Physics, I am a retired quantum physicist, and I have discovered an ingenious quantum technique that is worth $100 billion. Right? I will happily give you 50% of this if you will provide me with access to your bank accounts. All right. We all get these kinds of emails. Right? The previous emails were from engaged, interested, nice dogs who read the book. This one's from an evil squirrel, the kind that lurk in the trees outside our house. I used to set my dog off. Unfortunately, there are a lot of evil squirrels out there. There are people who try to use quantum physics in a cynical way to extract money from the gullible. All right? And this takes lots of different forms. All right? There are conferences out there on quantum healing, right? Which claims to be able to do medical miracles using the magic of quantum physics, right? You are simultaneously in a superposition of sick and healthy at the same time, and if you just learn their secret techniques, you can pick the healthy part and do that, right? This involves these sort of energy field diagrams that are kind of interesting. There's some new agey stuff that shows up. There are some things that show up that seem designed to cause headaches and nausea that you can then heal with quantum mechanics. Free energy is another angle that a lot of people take. Using this miracle quantum product, you can produce electricity from nothing, never pay an electric bill again. All right, this again takes lots of forms. It has some engineering sort of flowcharty things that look sort of convincing. Some of them are in Russian, which gives it a nice sort of Cold War flair. All right. My favorite examples of this, there's a whole bunch of these, is living a quantum life by meditating. You can make the universe provide for you, right? You have the secrets of manifesting. If you want things badly enough, you can make them appear, right? There's quantum selling secrets. The secret is if you put quantum in the name, it'll sell better. There's the laws of attraction. There's quantum mind power, right? All of these things are based on the idea that quantum mechanics is magic, that you can use this to bend the universe to your will. All right. All of this is crap, right? There are a lot of brilliant people out there who know a whole lot about quantum mechanics, and I promise you every single one of them is stuck writing research grants. Right? Wanting funding really badly does not allow them, their knowledge of quantum mechanics does not allow them to make money magically appear. All right. Quantum mechanics may seem extremely weird, may seem almost magical, but at the end of the day, it's a scientific theory. It comes with the things that you get with a scientific theory. It comes with math, right? It comes with sort of rigorously defined physical processes and patterns of regularities in nature that you can calculate to astonishing precision. Right? It is a rigorous and quantitative and well-tested theory of how the universe works. And it works really, really well. Right? This is a famous, slightly off-color XKCD cartoon. This curve here, right, is described by this formula. This is the very first quantum mechanical model ever constructed by Max Planck in 1900. It describes the wavelengths of light emitted by a hot object. Right? And this has been confirmed to astonishing precision. This slide right here is data showing that exact same curve taken from the WMAP satellite, measuring the temperature of the microwave background radiation in the universe. The red points are data. The blue line is the prediction of that formula, and they match perfectly. All right? This is an amazingly successful theory. And because it's such a successful theory, it enables us to do amazing things. Right? Because we understand about the wave nature of electrons, we know how electrons move through matter. And that allows us to modify materials to change the way that electrons move, which lets us make computer chips. We can make transistors inside blocks of silicon. And we can pack billions of them together onto tiny little chips to power our computers and our smartphones. Right? Because we understand about the particle nature of light, that light is sometimes a wave but sometimes behaves like a particle, we know how to make lasers. All right? And those lasers are used through fiber optics to make all the telecommunications connections that we rely on every day. Every time you use your smartphone, you're taking advantage of quantum mechanics twice over, through the computer chips and through the telecommunication lines that are powered by fiber optics. Right? Even something as obscure as tunneling has amazing applications. We can make a thing called a scanning tunneling microscope that uses this tunneling behavior to measure the properties of materials atom by atom and even manipulate them. Right? We can push atoms around on surfaces to make patterns and control matter at the atomic scale because we understand exactly how quantum mechanics works. So some of the predictions of quantum mechanics may seem counterintuitive enough that they feel almost like magic. But ultimately, quantum mechanics is not magic. Right? It's science. And the key difference between science and magic, right, is the absence of lying. All right. So anybody out there who contacts you trying to pitch quantum mechanics as magic, right, is not on your side. Right? They're trying to take advantage of you. If what they're selling as something quantum seems too good to be true, it almost certainly is not true. And the person selling it is probably an evil squirrel. So I want to end basically on that cautionary note. Beware of the evil squirrels out there. I also want to offer a tribute to my co-author, as it were, Emmy, the Queen of Niskayuna, who very unfortunately we lost her in December. And so here are some of my favorite pictures of her in my research lab. So she was a wonderful dog. She had a fairly long life for a dog. She was the best. I wouldn't be where I am without her. So miss her a lot. With that, I will say that I hope my talking about physics has not made you as sleepy as it sometimes used to make Emmy. And if you have any questions, I'd be happy to answer them. So, thank you. Questions? Yes?
You never did explain how we solve the Schrödinger's cat problem.
How do we solve the Schrödinger?
Why it doesn't really turn out.
So there are lots of different answers to that, sort of, right? So how do we solve Schrödinger's cat? The core assertion is that you really do get the results as if the objects are in two states at the same time. Now, there are different ways of approaching what happens inside the box, right? The sort of orthodox language that most people tend to use is that the particle inside the box is both alive and dead at the same time. It's in the superposition, really in the superposition the whole time. There are theories, though, where ways of interpreting that give you, it is really alive or it is really dead inside the box. You just don't know it. Those have some weird properties in other areas. So there are a lot of ways of approaching it. There's also the many worlds theory that says that your cat is both alive and dead inside the box. And after you open the box, the cat continues to be both alive and dead. It's just there's a version of you that knows the cat's alive, and there's a version of you that knows that the cat is dead. And the universe sort of continues on in sort of two parallel tracks. All of these different variations of approaches to understanding what's going on inside the box, all of them give you exactly the same prediction of the results in the end. So on some level, basically, every working physicist defaults to what David Merman called the shut up and calculate interpretation, which is you get the same answer no matter how you think about what's going on. And so most of us choose not to worry about it. But it's fun to think about those things sometimes. Questions?
You mentioned tunneling and the fact that the absence of tunneling is
So the question is that I asserted that it takes 15 billion degrees to make fusion happen, but the temperature is lower for the sun thanks to tunneling. And is that true for everything? I believe I am not an expert on the physics of nuclear weapons or fusion reactors, but my understanding is that in any of those contexts, you're probably relying on you're benefiting from that tunneling being there. So back there. So what's this have to do with the quantum supercomputer? So are you thinking of D-Wave? So there's a company called D-Wave that has made a device that does a particular computation. And there's some controversy over whether it's actually quantum or not. Right? They claim that they use quantum mechanics to do a certain calculation faster than you could do with a classical computer. And quantum computing is a thing that's very real. And it turns on this business of things being in multiple states at the same time. Right? So a classical computer, you have bits in your computer that can be either 0 or 1. And each is definitely in one of those two states. A quantum computer can be in an arbitrary superposition of 0 and 1 at the same time. And that opens up a wide range of additional possibilities for computation. There are certain kinds of problems that you can solve faster using a computer that can do that than you can with one that just runs on classical bits. So quantum computing is a very big deal. There are a lot of people who work on that. It has some major applications, the most famous of which being you can use it to factor really large numbers if you could make a sufficiently large quantum computer. So lots of people are working on that. Most of those people think that what D-Wave has is an interesting curiosity, but not really a quantum computer. The conditions under which they operate the machine don't seem like there should be enough quantumness in the calculation for it to be doing something. But on the other hand, it seems to work pretty well. So there's this back and forth as to whether it's really quantum or not. And I think the jury's still out on that. It's complicated by the fact that they're a commercial company, and so all of their hardware and algorithms and everything is proprietary, and so it's not very easy for people to study. But some people claim that you can write optimized code on a laptop that will do the same thing faster than the D-Wave thing does it. But there's a lot of arguing back and forth, and I don't think it's anywhere near settled yet. But when somebody eventually gets that to work, it'll be a very, very big deal. Yes?
How does this correspond with string theory?
So how does this relate to string theory? So string theory is an area of physics that's attempting to merge quantum physics that I talked about here with the other titanic theory of modern physics, which is general relativity. And general relativity deals with gravity warping space and time, right? And loosely speaking, works really well on very large scales if you're dealing with like big, heavy things or things that are moving very fast, whereas quantum mechanics deals mostly with very, very small things, right? So those two work brilliantly in their respective realms. The problem is there are some places where they ought to come together, and they don't play nice mathematically. Mathematically, they're very different objects, and if you try to push them together using the tools that people have developed for other things, it just doesn't work. That you get nonsense out of the math. So string theory is an attempt to get around that by asserting that quantum objects behave like strings that vibrate in multiple dimensions, right? And this is an area that mathematically has been very productive. People have put a lot of work into it, and there's some really cool stuff that comes out of that, mostly relating to results around black holes and relating you can make a connection between the way certain kinds of black holes behave and the way some superconducting materials behave. There's an interesting physical connection there. Whether it's actually a theory that successfully marries general relativity and quantum mechanics is still an open question. Nobody's been able to sort that out yet. What it'll really take to sort that out is getting a good look at the few situations in the universe where you really need both of those things. And that's largely things like black holes, where you need quantum gravity if you want to understand a black hole. So a black hole is something that packs an enormous amount of mass. So it's a big thing that warps space-time. That's sort of the realm of general relativity, but it packs it into an infinitesimally small area, which is the regime of quantum mechanics. So you want to describe a black hole, you really need quantum gravity. We don't have that worked out yet. We don't have a really good look at a black hole yet. So that's coming. I don't know if people have heard the rumor. There's rumors. There's a press conference scheduled for Thursday by an experiment called LIGO, which is the Laser Interferometer Gravitational Wave Observatory, excuse me. And they have scheduled a press conference for Thursday. They're trying to observe gravitational waves caused by things like two black holes spiraling together and combining into one. And people think that they may have detected such an event, and that sort of thing. That one event that they may be announcing on Thursday isn't going to solve the quantum gravity problem, but getting to see that sort of thing happen is the kind of thing that'll lead to useful information that we can use to test quantum gravity and see how that plays out. So it's an exciting period. Nobody knows for sure what they're going to say at their press conference on Thursday, but whatever it is, it'll be pretty cool. So, in the back there. Okay, so you're asking, so if electrons, we can't really say that an electron is orbiting in an atom like a little solar system, so how do we say that it's hitting a particular place on a screen, that sort of thing? It's a difference of scale. So it's true, we can't, if you tried to have an electron actually orbiting an atom, like a little solar system at sort of ordinary energies, it doesn't really, you can't really make that work because of a thing called the uncertainty principle, which says that if you know the position of something really, really well, then there's a big uncertainty in its velocity, right, and how fast it's moving. And if you try to put those together, you can't make an atom work like that. So what an electron in an atom really looks like is sort of a smeared out, fuzzy cloud of probability around that atom. All right. So how do I go from that to saying that I detected this electron at this position at this time? You know, the size of an atom is like an angstrom. It's like 1/10 of a nanometer. All right. The size of the spot on that phosphor screen is like, you know, a millimeter. Right. And so the uncertainty in the position of the electron that when we say the electron is right here at this time, there's actually enough uncertainty in that you're not actually doing anything all that. You're not really constraining it that tightly enough that uncertainty would mess you up. Right? So it's just the pixels on that camera are big enough that you spread the electrons out enough that it's not really invoking anything quantum. So does that answer your question? So, other questions? Yes. So how did I end up doing this? So this is the strangest thing that ever happened to me in my life. So I really did talk with the dog, and I would do her half in that silly Andy Kaufman foreign guy voice that is in the video, because it makes my wife laugh, and I will do a lot to make my wife laugh. So inevitably, physics started creeping in because this is what I think about a lot, and so physics jokes started appearing in those. And I was in a very strange mood one day, and I wrote a post for my weblog where I had a conversation with Emmy about the many worlds interpretation of quantum mechanics. And I wrote this up and I posted it, and it got linked by the tech blog Boing Boing, and 50,000 people read that post that weekend. One of the people who read that post was an agent who contacted me and said, you know, this would be a great idea for a book. And I said, huh? But I thought about it for a while. I'm like, yeah, this is a really, you know, good vehicle for talking about some weighty things, right? So the book has these, you know, funny conversations with the dog about aspects of quantum physics and how she might try to use them to catch prey or finagle treats from me, and I explain how it really works. And then there's a longer explanation in each chapter of how the physics works out with occasional interjections from the dog when the going starts to get tough. And it turned out to work really, really well. So it was completely by accident. It was not. I easily, you know, when I was a college student or a high school student, like I could picture myself someday writing a book. But a book explaining physics with a talking dog was totally not anything I set out planning to write. But you know, it's worked out pretty well. So. Well, the first one went well, so I did it a second time so there's a relativity book as well. So, but the weirdest thing that ever happened to me. So, yes. Yeah, entanglement. So the idea of entanglement is a big part of quantum physics, and I didn't have time to. There was a whole bunch of stuff that I didn't have time to talk about in this talk. Entanglement is this really powerful idea in quantum physics that says it's possible to make situations where you can have a particle over here whose state is not determined, and another particle over here whose state is not determined. But the one thing you know is that when you measure them, they'll be exactly the same. All right, so if you measure this one to have it spin up, this one will also have it spin up. If you measure this one to have it spin down, this one will also have it spin down. If you know, spin sideways, spin sideways. Right, they'll be perfectly correlated always. And that seems to violate relativity, right? That seems to be a situation where you're doing something over here that affects what happens over here, but in a way that doesn't involve sending a signal from one to the other at the speed of light, right? If you wanted to think of it in terms of signaling, you'd have to be sending your signal at speeds much, much greater than the speed of light. And that seems wrong. So physicists call this non-locality, right? So it's violating the principle that something that happens here should only be able to affect things in its immediate local neighborhood until some time has passed. It's a really weird idea, and this is another thing in the same time Schrödinger was doing his cat thought experiment. Einstein wrote a paper with two young colleagues where he introduced this idea of entanglement and said, you know, this is an indication that quantum mechanics has to be incomplete. And nobody really knew what to do with that for about 30 years, but a guy named John Bell in the 60s showed that there is actually an experiment you can do that will distinguish between the quantum prediction that things are non-local and weird and the sort of theory that Einstein preferred. And people have done those experiments starting in the 1970s and, you know, continue to do them today. And every time anybody's done those experiments, it shows that the weird thing is true. That you know, these things are really correlated in a way that does not respect the speed of light limit between the two. Lots of ways to think about how that happens, right? And you know, one of the ways of reconciling that is to say that, well, you know, all we really deal with is information, so it doesn't make any sense to talk about an underlying reality. And that's an approach that some people take. That's the sort of philosophical thing that bothered Einstein so much. But it really is a real phenomenon and something that people have to work very hard to understand. So.
What are the reasons I really like?
There's a theory, a way of doing quantum mechanics is called Bohmian mechanics or de Broglie-Bohm theory that does that sort of thing. It says that particles have definite positions and momenta at all times, but that they're pushed around by this guiding field that is sort of an extra wave that travels through the universe at speed, but that it's a non-local thing. It changes faster than the speed of light. And that is an internally consistent way of doing quantum mechanics. It's kind of weird, but you know, all of the ways that people come up with doing quantum mechanics are kind of weird. So that's a thing you could do. So, other questions? Science fiction recommendations recently. You know, people ask me this and then I go completely blank. Recent science, there's an astronomy book that I've been working my way through that's on the textbooky side of thing, but it's by Ethan Siegel, does a blog called Starts with a Bang, and it is like Beyond the Milky Way or something like that. But it's by Ethan Siegel from Starts with a Bang. That's a really nice survey of astronomy with absolutely no math in it, which is the best way to do astronomy. So, last question in the back. So there are ways. So you're asking about a thing called the measurement problem, or the sometimes observer effect, right? The notion that is implicit in the video that I started this with, where you open the box and that makes the cat inside pick either alive or dead, and so that the act of observing something changes its reality. That is one of the ways that people come up with to deal with the weird stuff, right? So I mean, the thing that's weird is not that you don't know what the state of the cat is while it's inside the box, because there's that sort of thing happens all the time, right? What's weird is the notion that when you open the box, you force it to pick one or the other, because we know that we only ever see live cats or dead cats. We don't see half alive cats, right? So one way of dealing with that is saying, well, the act of seeing it causes it to change, to pick just one or the other. And that's a whole class of theories that people do. There's another way of doing it, which is to say, which is many worlds, which is, the cat is both alive and dead. And then when you open the box, the cat continues to be both alive and dead. But now you are in a superposition of knowing that the cat is alive and knowing that the cat is dead. And, and the universe continues on with everything in a big superposition. And that also works perfectly well as a way of interpreting things. And so either of those, both of those, like I said earlier, both of those give you exactly the same predictions for measurements you can actually make. So, it's sort of an aesthetic choice at some level as which way you prefer to think about the universe working. At least until, somebody comes up with a way to distinguish. And I mentioned John Bell a little while ago talking about entanglement, right? There was this problem of, is this entanglement thing real? For like 30 years, nobody knew what to do with it. And he sat down and thought really clearly and rigorously and analytically about what exactly does it mean for these two types of theories to be true, and then can we find a place where they predict different things? And so, and that worked brilliantly, and you can do an experiment that tests entanglement and show that it's really a thing. It's still an open question whether there's an experiment you can do that tests whether, observing something causes a physical change that makes it pick one state or the other, or whether the universe remains in an ever-expanding superposition. Somebody may come up with it someday. Nobody has yet. So
far, they produce results.
Absolutely. And the results that you predict work to 15 decimal places. So works spectacularly well. It's just how do you interpret what's going on inside the box? And that's kind of, at this point, is still essentially an aesthetic choice. You can pick whichever one you like better. So I think we're out of time. I'm happy to answer questions down here. People have more questions, or thank you all for coming out. It was fun.